Is this okay for everyone? Oh, okay. Yeah, thank you so much for that very kind introduction. I'm very happy to be back here. I guess I will also say I've spent a lot of time here at FRIB. Um, I was here first in 2019 as an RU student, where I was working with Morton. I don't think he's around anymore. I think he ran off to Norway. Is that right? Yeah. And then I was back in 2022 for a few months where I was having lots of discussions with Dean Lee and Scott Pratt. And I've been here for multiple workshops and summer schools, and I have many good friends here. Um, yeah, so this is a very special place. I'm very happy to be back here now as a seminar speaker. So today I'm going to tell you about the equational state of QCD in the context of neutron stars. And I'm very happy that I don't have to convince you to care about QCD. I'm writing postdoc fellowship applications right now, and some faculty was giving me feedback on some of my proposals, and he said that I wasn't doing enough of a good job convincing people to care about QCD. And I was so upset by this because I think it's the coolest thing in the world. What do you mean I have to convince people to care about it? It's a given. It's so cool. But I think it also is a field that has such a rich landscape. Just here at FRIB alone, there are many things you can do. You can think about QCD in many different contexts. You can think about QCD as a perturbative theory where you have these particles and individual interactions and you're calculating perturbations about a free gas. You can think about the structure of an individual bound particle, something more like EIC physics. You can think about the landscape of isotopes. You can think about the shape of nuclei. You can think about nuclear structure inside nuclei. But what I'm going to focus on, and I guess the common thread between all of what I've worked on as a graduate student is QCD as like this equilibrium matter. So thermodynamic limit. And I'm going to specifically be talking a lot about phases of QCD and the phase diagram. So I wanted to start by motivating that a little bit. This landscape that I was talking about, of course, is richer. I just took some snippets from the long-range plan of some of the different subfields in our area. But this is where I sit. I study the phase diagram, equilibrium, QCD matter. So we're assuming things are very nice and equilibrated, which of course doesn't correspond to reality most of the time. Okay, why is this interesting to study? So the information that is contained in a phase diagram is the phase boundaries and the physics of the different phases in thermal and chemical equilibrium of a theory. So typically in QCD, the representation you're going to see is you're going to have some temperature axis, and then usually baryon density or baryon chemical potential, because that tells you how much baryon matter you have in your system. I will also talk about this additional dimension a little bit later. But the point is you can map out the properties of your theory as a function of some special thermodynamic variables that you expect to vary in your system. And phase transitions represent singularities in this phase diagram, so where something changes. And these phase transitions, these changes in degrees of freedom and interactions in your system, they are going to leave thermodynamic imprints. So that is something that is going to be represented in the phase diagram, but this is what we care about, is the fundamental degrees of freedom in your theory and the interactions between those degrees of freedom. And this is something you can study, represent with this phase diagram. Okay, so why am I talking about neutron stars specifically? And I guess talking with my hosts a little bit before the seminar, I think I should say a few words about neutron stars because not a lot of people here are familiar with those objects specifically. So neutron stars are formed when very massive stars collapse. There are this stable state that you can form because there was enough pressure in your system to counteract gravity, so you don't collapse all the way to a black hole. You end up with this ultra compact object. And I'm going to talk about why you have neutrons and why they're called neutron stars in the next slide. But the point is, these are super compact objects. So the densities that you reach in the core of a neutron star are up to several times that of a nucleus, which is already quite dense. So let me also just say, what do we actually know about the phase diagram of this very fundamental theory? And perhaps not surprisingly, because QCD is so difficult, the answer is not a lot. Well, we can know a lot about it in specific regimes. So I would like to highlight a few different regimes. First, you have nuclei, where you have facilities like FRIB, where you can get a lot of information about what's happening with nuclei, and there's a bunch of things you can study there. Then at much higher temperatures, and here we're talking in the scale of MeV, so this is very, very hot. These are temperatures that are achieved in high energy heavy ion collider experiments. And there you can actually use lattice QCD if you're at sufficiently high energy. So you can treat quarks and gluons on this lattice, and you can compute the properties of this system in equilibrium on the lattice. The problem is that you run into numerical and sampling issues as you add more density to your system. So lattice QCD has a limited reach on the phase diagram. It only covers this region here where your density is sufficiently low for your simulations to work. From lattice, we know that at some point you go from having a hadron gas in your system to a quark-gluon plasma, so you have that transition. And from lattice, we also know that the nature of this transition is something very specific that I will cover in a little bit. So we know about that, and we have systems that we can create in labs that exist in this region, so that's nice. But there are a couple issues here. First is that now we're going into experiments that can actually collide ions at a lower collision energy, meaning that you will have a higher baryon density in your system. And in that region, we don't really have coverage from lattice QCD. We actually don't know what the correct description is in that region, somewhere around here. And for neutron stars, you're in a completely different region of the phase diagram. I'm going to explain how you get to this band in a little bit. But we also have no idea what the correct description is for most of a neutron star. So they are very interesting objects because they exist in nature. They are relevant for phenomena that people study, like massive star collapse and star formation. But we don't know what the correct degrees of freedom. We don't know how to treat these objects. So aside from that perspective, I also think it's just really cool that we could have undiscovered phases of matter hiding in these things. So I guess in order to move forward with my seminars, I usually have a slide just to get everyone on the same page about the language that I'm going to be using. I think that's usually the biggest barrier in seminars and talks is when people are not speaking the same language. So I try to go back to a level that is like grad school and then develop all of my logic using that language. So this is a review of statistical physics. I don't know about here, but in Illinois, we're all required to take it. So I assume that at some point you saw this maybe in undergrad, but I'm also happy to take quick questions during the seminar if they arise. So I call this slide phase transition phenomenology because it's the language that I use to talk about the phenomena of phase transitions. So in general, a system in thermal and chemical equilibrium, like I was saying before, can be described by thermodynamic state variables. Those would be whatever axes you chose to be on your phase diagram. And sorry, the axes are the independent variables, thermodynamic variables, and the state variables are things like the pressure, entropy, energy density, chemical potential, number density. So basically how the state of your system responds to changes in your thermodynamic variables. And there is a special relationship between these things that encompasses the underlying theory, and that special relationship is the equation of state. So you can represent the equation of state in a few different ways, but for instance, you can talk about the relationship between the pressure and the energy density, how one responds to changes in the other. And phase transitions are characterized by the lowest order derivative of the free energy, which is discontinuous at the transition. So this is related to the imprints I was talking about earlier. So if you have a phase transition, you can look at this quantity, which is called susceptibility, a derivative of the pressure. And if you find discontinuities in that derivative, that will tell you about the order of the phase transition. So how you're going from one phase to the other. That doesn't mean that every time you have a change in phase, you're going to find discontinuities. That case is a crossover. So if you take derivatives of your pressure and you get that it's infinitely differentiable, that's a crossover phase transition. But if at some order you find a discontinuity, that's an nth order phase transition. So something that has a phase boundary, like ice to water, that's a first order phase transition. You can have a system that has the two states and there's a boundary between them. Any questions about this? I think this is all the language I need to set up the problem. All clear? Everyone remembers stat phys? Physical space, yeah. So you have like a bubble of a different phase, like you would have a boundary between the two things. Yeah. In the equation of state, the way this is represented, I'm going to get to it later, but it's a discontinuity in density. So like the density of water and ice is, there's a jump between them. Okay. So what exactly can we learn about the phase diagram from neutron stars? Because it's not this like magical probe that will answer all of our questions about the QCD phase diagram. It's actually going to answer a very specific question about the phase diagram, which is illustrated in this figure that I've been using by this band here. You'll notice that the figure that I'm showing you has 3 independent axes, but that neutron stars sit basically on a line with uncertainty. So why is this space so reduced? And that is because the actual system that is realized in neutron stars will have some additional constraints. So it's not going to probe everything. It's going to probe a region that obeys a set of constraints. The first constraint that you have is that in a neutron star that's been sitting there, it's not doing anything crazy. It's had enough time to reach a thermal and chemical equilibrium. Actually, the Fermi temperature of that system is so high because it's so densely packed that all of your particles are going to be sitting at the lowest energy level. So that means that you can assume that the temperature of the system is 0, even though neutron stars are actually hot. It has to do with the Fermi distribution and the shape that it takes. Actually, neutron stars are very hot. I put the number there, 10 to the 8 or 10 Kelvin. So very hot, but effectively for thermal physics purposes, 0 temperature. You also have this condition called beta equilibrium. And that happens because as you start packing nucleons, so protons and neutrons, at some point it becomes energetically favorable to convert protons into neutrons. So that's how you end up with an abundance of neutrons and the name neutron star. And the further you are into the star, the denser you are, the more favorable it is to produce these neutrons. And the exact like equilibrium of that relation is what's going to give you the beta equilibrated line. Now, I will note that the reason we represent this as a band and not a singular line is because there is uncertainty about the composition of the star and what exactly this line is. But in principle, it is a line on this plane. So 0 temperature with some beta equilibrium. And then additionally, you have the condition that the star is not globally charged. So you have this electrical neutrality condition. And this is not going to be so important for me today. What is important for me is that you know that even though there are 3 variables that are relevant, I'm actually working with something that is one-dimensional because of these additional constraints. So we're only treating things as a function of the density because everything else can sort of be constructed away. Okay. So I'm going to talk about how we can learn about QCD from these stars now that we know what we're actually trying to learn. And it's actually a very easy problem in principle. Like Agnieszka was saying, I have a background in heavy ion collisions, and the simulation pipelines are a nightmare. And to infer anything from any observable, you need this like massive computational setup, and it's just a nightmare. This is a lot simpler because you have observables that map directly to your equation of state. So basically, for any equation of state, I can calculate uniquely for a given mass how big that star will be. So that's my equatorial radius. And how squishy that star will be, how it will respond to tidal deformation. And that's my tidal deformability. So I'm illustrating this here with a couple of equations of state. A common representation you will see for neutron stars is we'll talk about the speed of sound as a function of density. And that is because those phase transitions leave very clear signatures in the speed of sound, as I'll discuss in a bit. But for any given equation of state, I can uniquely map this relationship where I pick a central density for my star, and then I can predict exactly what the mass and the radius of that star will be. And that gives me this mass radius relationship, which you'll also see a lot in the context of neutron star physics. And I can do this for a number of central densities such that I map this entire relationship. And at some point, I will create something that cannot resist gravitational collapse. So that's the point where you would cut off your equation of state, because at that point in nature, if you try to realize that system, you would just have a black hole. So that's why this relationship stops at some point. And this depends on the equation of state, so you can always do this map. The problem is, when I actually perform a measurement. So let's say we discover a pulsar today and we name it PSR FRIB 2025. I do this for every place I go to, I'm sorry. And we name it and we measure it with some uncertainty on the mass and the radius. Okay, that's basically what equipment is doing out there. Real observational experiments are doing out there. I cannot map this observation uniquely to an equation of state, because there is a huge degeneracy of curves that go through my observation because of the uncertainty. And also because I'm only probing one star, one central density, one mass. So for me to actually be able to invert this problem, what I would need from astronomers is that they measure every possible neutron star that can be produced with infinite precision, which is unfortunately not how this works. So instead, the standard approach is you come up with some model for your equation of state. You map that to your observables, because you can always do that. Then you compare to data that you have in any theory that applies, and you see if what you predicted is compatible with the information that you have. And this is typically done in a Bayesian fashion, so there will be an inference setup where uncertainties are accounted for and all those things. So that is the business of what I'm going to be talking about today, is how do we produce these models? What goes into producing those models? What are the tricky things? And what did I learn from studying this problem? Okay. So it would seem that because the setup to go from the equation of state to observables is simple, that maybe I would also get some free lunch with the modeling of the equation of state, but that's not the case. This is actually a very, very difficult problem. So the relevant scale here, I already told you we're talking about the baryon number density. The relevant scale in the baryon number density is the nuclear saturation density. Okay, so roughly, I'm going to take this to be 0.16 inverse Fermi cubed. There's some uncertainty around this number, but just for the sake of units, this is what I'm taking it to be. And if I actually looked at a star, if I took a core sample of a star, I should expect to see something that looks a little bit like this, where you have a crust, where you would have some description of matter. So generally here, densities are not high enough that you're like reaching the drip line or any, you still have nuclei. Then as I get deeper into the star to higher densities, some weird things are going to start happening. You're going to have an excess of neutrons in your system, at some point your nuclei are going to start melting such that you have neutrons and protons, but they're not really forming nuclei or any like structure that we're familiar with here on Earth. And then at some point you transition to the inner core, where you can have a gas of neutrons and protons, but maybe other things. So in this regime, where we have something that looks closer to what we have here on Earth, there are effective theories available. I think lots of people here study this type of matter. So you can work within those models. You can be relatively confident that they should be the right description of things. But as you go into the inner core, we actually have no idea what the relevant degrees of freedom are. So it's not only that we're working with a theory that has uncertain parameters, the theory itself is completely uncertain. And if you want to account for your uncertainty in your equation of state, you have to account for this uncertainty of we have no idea what the correct description is. Aside from that, I want to mention like a technical challenge that we have that was sort of unexpected that I guess Muse's collaboration, which is a collaboration I work with, figured out recently, or at least calculated it and showed its effect, which is that you have all these different physical descriptions and you need to stitch them together into a cohesive equation of state. And the way you stitch them together introduces uncertainty in your model. So this is not even something people were tracking before. And here we're representing this in the mass radius relationship. It is still within measurement uncertainties, but it is significant. They're not compatible with each other within uncertainties. So this is an uncertainty that you have to account for that is just numerical. It's just like, in what variables do I glue my models together? And until, I guess, last year, this is not something that was talked about in the field. That's a great question. Some people care about how you glue things to not introduce things that would have like it would correspond to a physical phenomenon. Like if you have something sharp that corresponds to some phase transition, especially in the speed of sound. But some people don't care. So it has been done in like a way, I guess the argument is that it's within measurement uncertainty, so it doesn't matter. But we would like to not introduce physics that's not physical into our models. And I guess my point is even the way you try to do that introduces uncertainty in your calculation. That being said, there are works where things are just glued together and it's sharp. And maybe it doesn't matter for the question that's being asked in that particular paper. Okay, so my talk will actually focus on this inner core region. And I'm going to talk about how models can be constructed for this and how we can compute the uncertainty. This is also a very difficult task, though. The point of this slide is to sort of highlight how difficult this problem is to model and how it's interdisciplinary within nuclear physics, and also just numerically tricky. And just know that everything we talk about from now on will be about this region. So just to summarize the logic of the problem, and this is not the only way to approach this. That's why I included the, in my opinion, at the top. Why I think this is important and why I spent a couple years looking at this during my PhD. So the big problem is that we have these huge gaps in our understanding of the QCD phase diagram, and neutron stars are this very unique probe in a region that is theoretically inaccessible. And we have measurements with uncertainties. So the task, the way I see it, is to translate those uncertainty measurements, so like mass radius measurements, into uncertainties on the equation of state. And then I think a later but necessary step to retain the connection to nuclear physics is to think about how different models fit within the uncertainties in the equation of state. So I guess the way I see the flow of the problem is sort of, we need to compute this uncertainty first, and then we need to go backwards from the models and ask what models predict things that are compatible with the uncertainty that we extracted and within what parameter space of the model. And then we can start, I guess, making our guesses about what the correct degrees of freedom are in interactions. Okay, so I'm gonna need to get a little more technical for 1 second. Because I basically just told you that we have no idea what's happening. So we need to account for seemingly an infinite number of possibilities. How do people do this? So the idea is that you have instead of having a model with some parameter space that you're just plugging in all the possible parameters and seeing what it predicts, is to have a statistical sampling of the functional space corresponding to the equational state, because that frees you from the shackles of whatever degrees of freedom are in specific models. There are different approaches for how to do this. This is just one, and I think it's a cute one, which is to use Gaussian processes. And I think that's something that people use in many different contexts, here at FRIB included. But the way that I'm using it is to draw samples from a statistical distribution of functions. So that's the goal with introducing Gaussian processes. And I guess the mathematical definition is that you have some function you're trying to sample. And this function at each point you're interested in sampling will have some mean value and some covariance with the points surrounding it. So at each point you have a distribution which is Gaussian, but it is also correlated with the points around it. An important thing to note here is that a Gaussian distribution has infinite range, and thermodynamics doesn't allow for an infinite range. There are certain things you have to respect in thermodynamics. So we need to bake that information into the sampling of our function. The way we do this is by mapping something which is distributed like a Gaussian, so this function I'm calling phi, into a limited range. So by establishing this relationship between the function I'm sampling from and the speed of sound of the system I'm sampling, I ensure that the function I'm producing corresponds to an equation of state that is stable, causal, and thermodynamically consistent. So that's a technical detail that doesn't matter as much for the story I'm trying to tell, but just so you know, I'm not doing something insane. I am sampling things that thermodynamically make sense. And this procedure was not our idea. It's been around for several years at this point. It's just a method for sampling functions. You could have come up with any other method you wanted, and people have done a few different things. Okay, so to specify the properties of this distribution, you need to make a couple of choices. The first one, of course, is what is the mean? And the second one is how are the points correlated to each other? And in that, we saw an opportunity to maybe translate some physics into something that is general, some nuclear physics into something that is general. Okay, so to motivate what we did, I want to talk about models for a second. Before we did this work, the sort of common approach, maybe I can show this plot. The common approach was to just pick some numbers for these hyperparameters in my distribution, maybe test a couple of different choices, see that what you extracted was compatible and it didn't matter that much what you chose. And then look at this posterior band. So just look at the bounds, right? So what does my posterior correspond to in this space of the equation of state? But then if you looked at the individual functions that make up this distribution, this posterior distribution, the way they looked wasn't quite compatible with all of the nuclear physics models that were available. And in particular, they were not compatible with physics models that had interesting new physics. So I want to outline that argument a little bit better now. Here is a compilation of nuclear physics models that do make assumptions about the degrees of freedom. So some of them predict that you only have protons and neutrons, and they interact in some way, but you never make any new degrees of freedom. Some of them predict that you get quarks. Some of them predict that you get strange baryons. Some of them predict that you have specific meson interactions, whatever. All of these interesting things you can do when you write down a Lagrangian or a potential or something. And when we looked at those models, their representation in this like speed of sound density space was very funky. So whenever you had new degrees of freedom appear in your system, you would get all these like weird kinks and plateaus and things that were not like a smooth curve. And when you looked at what these samples were producing, they were all very smooth curves that didn't encode any of these interesting features that were being predicted by the actual nuclear physics models. So what we did was to look at this and ask if we could modify our sampling procedure to introduce features that look like this so that maybe we can have some connection to models and specific nuclear physics in this like very agnostic sampling of functions. And maybe then we could see if data tells us something about which of these models are more compatible with data. So the way we found to describe this behavior is that you see that there is some like long range correlation between points in this function, right? They all seem to be generally increasing with density. So that's the long range behavior. But locally, you have these like funky kinks, bumps, and plateaus and first order phase transitions and things like that. So the previous modeling, which only included this long range correlation, is not necessarily incorrect, but it's, if you want to represent undiscovered phases of matter, you need to do something different. So that's what we call modified Gaussian processes, because we took something that existed and then changed it a little bit. And the modifications are these imprints, thermodynamic imprints, that are compatible with what the models were predicting. So there's a few categories of these things. I'm going super slow. Okay, let me speed up. There's a few categories of these things. Some are compatible with crossover phase transitions, and some are compatible with first order phase transitions, and you can have these things at different densities. And this is very nice because you can sample these things, so it's Bayesian friendly, it's not attached to a model, all of these things. And you can specifically also do Bayesian model comparison. So you can ask the interesting question of, if I include these features, if I model the onset of exotic degrees of freedom versus if I just sample smooth functions like people were doing before, is the data going to prefer one over the other? Okay. So I guess what I want to say with this slide is that we did this and we checked that the samples that we were producing they looked like what the models were predicting, right? So we were hoping to represent all of this funky behavior with our sampling. And when we do our sampling, we check that, yes, in fact, we reproduce all of this funky behavior. So then now it's a different question whether or not data can distinguish between these two cases. And that's exactly what we did next. We performed a Bayesian inference study with all of the data that was available at the time. And we got posteriors for both of the different models. So the model that included our modifications versus the benchmark, which is what other people have been doing before. And we found that there was some difference if you just looked at the, oh, this is cropped. This is still the speed of sound. If you just looked at the speed of sound as a function of density. But this doesn't seem to be the right variable to look at, or the right way to look at it if you want to see differences, because the data is just not that informative. Another sort of pseudo-observable that we looked at that turned out to actually be interesting was the baryon number density at the maximum value of the speed of sound in the star. And what that tells you is if you have sort of a peak in your speed of sound, and then it goes back down within the star, that could, according to predictions that have been made by models, represent that you're going through a crossover phase transitioning, and that softening of the equation of state, that dip in the value of the speed of sound, corresponds to a new degree of freedom entering your system. So the pressure is going into producing, the energy is going into producing these new degrees of freedom, and that's why you have this specific signature. So we were looking for that, and it turns out that if you use the model that didn't have all the funky features, that varied very slowly with density, you were suppressing samples that could accommodate for that type of physics. But in our version of the Gaussian process, the modified Gaussian process, you had enough flexibility in your sampling to produce functions that did that. And then it turns out the data does say something. It's not much, it's definitely not conclusive, but it seems to prefer that if a crossover phase transition happens, it should happen within a range in densities. And that is what is represented here. So this is just illustrating the difference between the two models, and you see sort of a peak in the posterior at a particular density where you could have this crossover occur. Should I wrap up? Is 11:35? Sorry, 39. Yeah, so the left is showing you, yeah, sorry, I was pointing all over. The left is showing you that your prior is producing things that your other prior wasn't producing. So basically, this is just illustrating that our sampling is producing samples that the other sampling is not. And that this is something that the posterior picks up as like a higher likelihood model. 5? Okay. Let's see what else. Okay. I had more things that I could cover, but I think 5 minutes. I can wrap this up. So I guess the last thing we did in this exercise was to compute the base factor, which basically integrates over all of the models you produced in one approach versus the other. And then when you take the ratio of how likely the model is collectively, you can tell if your data, or you have a metric to tell if your data prefers one approach versus the other. And in this case, the base factor we extracted indicates that currently our data is just not informative. And I have a slide about why that's the case. We just don't have a lot of data, basically. There aren't a lot of points, and the uncertainty is high. So we can't say much. That's not surprising. But I guess the point is these multi-scale correlations that we included, they turned out to be important in the analysis. Like I said, right now, they're not required, but they're also not ruled out. So they should be included as a theory uncertainty in the analysis. And there is a direct connection to nuclear physics models with our sampling, because we are modeling these thermodynamic imprints that you can then connect back to models instead of just having this function where you're like, okay, I guess this is the behavior, but does it correspond to any type of physics? This was an approach that we developed a couple years ago. And I guess just to emphasize why this exercise is important is that, again, we have this unique probe of QCD in a theoretically inaccessible regime. We cannot recreate it here. This is our only probe of QCD in that region. And in order to actually learn something from our measurements, we have to properly quantify our theory uncertainty. I think the crowd here is not that resistant to that idea. I know a lot of people do work in quantifying theory uncertainty, and you understand why that matters. But in other venues, this is a tougher battle to fight. So this is really important. It's the only way we can connect our measurements to real models. The last two things I want to say is this type of study has been repeated by many groups with different approaches. And I wanted to highlight that there is sort of like a coherent picture that we all agree on, right? Like we might disagree on the details of what's important, what isn't, how you produce these models. But as far as like if you're outside of the field, what is my field saying about this thing that I'm saying is so important? And I would say this is the consensus, is that our posteriors right now are sensitive to changes in the modeling assumptions or our priors. So that means our data is not yet informative with respect to these details in the equation of state that I was talking about. Where do I have that slide? Okay. So here I just wanted to lastly say that we are working with very limited information. So as far as data goes, we have these 2 points on the mass radius curves that have been measured by NICER, that those points entered our analysis. We have 2 tidal deformability posteriors from gravitational wave measurements. One of them, GW 170817, which was the first binary neutron star merger, the event that most people know. That is more informative than this other one, but neither of them are very informative. We have measured neutron stars with high masses, so we know that we should be able to produce, whatever equation of state I have, should be able to produce a star of at least 2 solar masses. From low energy physics, you can bake in some requirements on what the symmetry energy is in your equation of state. So we did that. And then from perturbative QCD, there is very little that affects this analysis because QCD is not perturbative until much, much, much higher densities than what is realized in a neutron star. But we do have thermodynamic inequalities, so you can put some bounds on things. That's what we have. We don't have a lot of data, and it is very uncertain. So this task is very difficult. You can ask me later what I think alternatives are, but I think for now, that's what I wanted to say for my talk.
The observables that are mass radius, no stars, to the mass radius curve. Before that, you have the calculation of the equation of state that also involves the speed of sound. Before that layer, you have all these models, and you're happy with some of what these models are giving in terms of flexibility. So you decide to cut a scissor somewhere in this pipeline and say, I'm going to replace the input that's coming from models by this machine learning approach without the process. Forward by trying to learn how to make my Gaussian process look like realistic outputs that could have come from models.
A+, the perfect.
There's a way where you cut with the scissors before that. So instead of trying to predict the equation of state to then input the mass radius, is there anything that you could make for machine learning to look like the way that the models produce the equation of state? Before in that pipeline, that might be easier to get realistic shapes.
Okay, so I think what you're saying is instead of modeling and sampling functions that are at the level of the equation of state, you want to model and sample functions at the level of the observables.
No, actually, the other direction.
Other direction. You want to go back to the models.
Yeah.
Like building emulators for what the models produce for the equations of state.
Sorry. Making the models go faster is trying to make machine learning instead of directly predicting. This is kind of like latent spaces that transform into other latent spaces and eventually all the way up to the equation of state, to the mass radius curve. Is there anything that you could do beforehand that might be easier to model with machine learning approach instead of direct output of the equation? If the question doesn't make sense.
No, it does make sense. I'm trying to think of if there's anything that would be like useful to model in that way. I think you could, but I also think that modeling the equation of state is the sweet spot because you have a connection to the observables and the physics, while not being restricted by specific physics predicted by specific models. I don't know what you would gain by going one level back, but I can think about it. Yeah. Thank you. Yes. Yeah, so what we did that for our model because we could track like exactly what we were introducing. The base factor is one, like all across, like every combination you can make. And it makes sense, right? Because these things that we're putting into the equation of state, they are at the level of the speed of sound, which will then be integrated to be a p epsilon relationship, which is then what goes into the TOV equations to give you a mass radius curve. So you're integrating a lot of this fine structure. So something that looks like this on my speed of sound, like a very obvious feature, if I integrate this to the p epsilon, is just going to be a small kink. So for my data to be sensitive to that small kink at that specific density, I would need to measure something with very small uncertainty at just the right mass. So I think it makes sense that we cannot differentiate this because we have data that's very uncertain and we don't have a lot of it. So in a sense, it was also kind of a proof of principle of maybe the reason we're getting these posteriors that look nice and tight is because we're not modeling the full range of the behavior we could have in the equation of state. Yeah, people have done this with different models. I think the easiest thing would be with first order phase transitions, because they leave very dramatic signatures in the equation of state. There is a study by Reed, Essek, and a range of collaborators where they did like a simulation campaign of gravitational wave observations. So let's assume that we have, instead of like 200 gravitational wave signatures with the same strength in the signal as 170817, which is the stronger one we have right now. What can we say? And what they concluded was the only thing they could say is they could place a bound on the latent heat associated with the first order phase transition, but it was a bound so wide that no models were predicting such a huge latent heat. Yeah. Thank you. Yes. Yes. Uh, right. So a kink up was the way that we found to model features that were very narrow. So like physics that exists in a very narrow range. Um, so something here like this triplet model, I'm not sure what phase this is. I think it's a color superconducting phase that exists for only a short range in density. So you have in between, you have that phase in between two first order phase transitions. You can model something like that. Um, Also in quarkionic models where you can sort of tune what your crossover looks like. I think there was a study by Larry where they had this like very, very narrow peak in the speed of sound. So this also corresponds to something like this. Yeah, I won't say about what I believe or what I don't believe is plausible. We were just trying to cover the full range of what models were predicting. Yes, they are sampled with some probability distribution that is in the paper, and I don't remember. It's kind of even, like which one of these are going to get. We also mix them. A tricky detail is that you can introduce these things and end up producing different features. So you can have, I guess, if you introduce something that is a plateau down, like I'm saying here, showing here, um, maybe this could interplay with like a peak up and you can have some like funky structure. So it's not necessarily like my prior sampling of the features corresponds to in my samples what I am going to get with these correlations and this funky behavior because they talk to each other. Yeah, that's our benchmark model. So that one was the sampling the way it's always been done by everyone else, where you just have smooth function. Changes in the core. Um, Oh, I see what you're saying. So all of these things are going to be related, of course, to the mass radius curve. It depends what mass you're at. So if I have a very low mass star, and if the central density of this star is not high enough to reach the density where I have interesting things happening, then it's completely degenerate to the mass radius curve where nothing happens at higher densities there. I'm not putting that into my sampling. My sampling will sample it equally, but what I get in the end depends on the measurements that I have. The two measurements that we have right now are at 1.4 and 2 solar masses. So if there's anything happening above the 2 solar mass mark, you're not going to be sensitive in your posterior to any of that. We did PQCD. I think you're familiar with the language, the PQCD constraints where you have to like pick termination density for your PQCD to be. Yeah, we picked the termination density to be the max central density of the star. And that is because, let me go back to the slide. That's because that's the highest scale relevant to our problem, right? So we're modeling neutron stars. We're not modeling anything above that. So we ask if whatever we modeled is compatible with PQCD at those densities, typically between 5 and 7 times saturation density. So PQCD was not very informative because, of course, you're going to be more sensitive to PQCD at higher densities. Oh, sorry. And then about Chi-rho EFT, we didn't put anything in. But with the way that we constructed our equations of state and having the symmetry energy in there, I think they would be very compatible with the 2 sigma band from all the predictions that are available. Yeah, but then that also depends on when you choose to stop believing chiral EFT. So if I take that number to be 1.1, maybe 2 is fine, and then 1.5 is the problem. We don't put anything below, I think, 1.5. Everything that we're adding in is above 1.5. We didn't want to mess with the low density region too much. Oh, hi, Jerome. 27. Mm-hmm. Yeah. Yes. Yeah, that's a good point. Okay, so the point of this slide, which I didn't include in the main talk, is just to show that we can reproduce the observables, which was the first sanity check. But what you're asking is here, there's a narrowing, right? Yeah, so this PDF is actually a weird one because most people show all densities, right? An equation of state for all densities. We are truncating at the max central density. So the reason this narrows is because I don't have a lot of points, a lot of equations of state that reach this density within the stable neutron star region. The ones that do are very stiff. But the bulk of them are going to die right here, where it's pretty wide, I would say. This is also the benchmark model, and you can see that with our features, this widens a bit. Yeah. Yeah, because to construct our benchmark models, we picked the same hyperparameters that Cole Miller used in his nicer analysis of the equation of state. One, because that's like an important analysis, right? It's the nicer collaboration. But two, also to kind of show that those choices were They're not the most general choices you can make. And based on the choices he made for the Gaussian process, you produce things that increase linearly with density. So you're always going to end up with like very stiff equations of state. We tried to relax that a little bit by introducing a second set of hyperparameters for the benchmark model that were a bit softer, but most of those failed to reproduce observations. So you just end up with the very stiff ones. Yeah, yeah. I think certainly that makes sense. And people have done this many, many times where you just pick a model, you sample across your parameter space, and you see what region in your parameter space is compatible. The reason we didn't do it this way is because one, I work in phenomenology, so I'm not interested in attaching myself to a model. But two, I think that all you can say from an analysis like that is what parameters in your model fit the data. And I think that's a fine, perfectly fine question to ask, but it's from what I described to be, the way I saw the logic of the problem is not the way that we approached it. I think, like I said, you can certainly go back to any particular model and ask if they're compatible with the uncertainties we extracted. Yeah, that's another way to. Yeah, I think it's a question of how you're sampling. I think you can definitely pick like a number of fragments and like a particular sampling across like each segment that would maybe give you something that's equivalent to a Gaussian process. Because in the end, you're just sampling points on a line. My concern, although I haven't like personally done any calculations to verify this, my concern is that those models are being used in studies that go to much higher densities, in particular studies that connect to the PQCD regime. So you're talking about modeling the equation of state across 2 orders of magnitude in density, and you're picking 5 segments. So you're introducing regions that are extremely correlated with each other, where maybe you're being a bit inflexible with the physics that can appear inside a star. Because as you can see in the models, this is a very narrow range in density. Like if we're talking about PQCD, this will go up to 40. And there's all this rich structure in the functions. So I'm concerned that it can't capture that. Yeah. Yeah, you could do that. It's kind of it becomes a sampling pain because you have all these, you're individually sampling all these fragments. So like now your sampling space is very high dimensional. They are independent, so you could do it, yeah. Mhm. Thank you.